Hi, my name is Naomi Park. I'm from Greenwich High School, and before I start, in case I don't have enough time, I'd just like to say thank you so much to CT-JSHS for giving me this opportunity to present and share my research.
That's very kind. Go ahead.
So my research is entitled Biomimetic Removal of Microsphere's Water Contaminants via Calcite-Infused Coral-like Melamine Sponges. So what is my project really about, and why should we even care about this problem in the first place? Well, the most prevalent type of marine debris is plastic, and plastic particles less than 5 millimeters in length are classified as microplastics. Microplastics most notably result from the degradation of larger plastic debris. So basically, instead of decomposing, the plastic will tend to fragment into smaller pieces, resulting in the creation of these microplastics. And the real detriments of these plastics are their small size, as they are able to easily flow through water filtration systems, nets, and more. Furthermore, this poses a significant threat to marine ecosystems as they block the digestive tracts of many marine and freshwater animals, diminishing an urge to eat and therefore causing some to starve and die. Recent literature by Martin et al., however, points out the potential and possibility of using Skeletorrhenia coral or stony corals as microplastic sinks, and their results depict that passive removal through adhesion to the calcium carbonate structures is 40 times higher than active removal through suspension feedings. Furthermore, recent literature by Valia-Vitil et al. Points out that through calcium carbonate nucleation, the calcium carbonate is able to essentially latch on to these microplastics and trap them. Although coral has the great potential to be a microplastic sink, destroying them for the purpose of microplastic remediation would be extremely counterintuitive. Now, this leads me into my engineering goal, which is to investigate and develop an artificial coral sponge that successfully mimics the coral's ability of microplastic retention, is stable and safe for marine life, as well as a cheap, effective, and efficient microplastic remediation device. Throughout my research, what I found is that microplastics are extremely hard to quantitate, not only in solution, but in general because of their small size. Therefore, I intentionally purchased and used green fluorescent microplastics throughout the entirety of this research because they are easily detectable via fluorescence spectroscopy. I then found their ideal excitation and emission characteristics in solution to mimic the microplastic contaminated water. I found that the peak excitation was at 455 nanometers with an emission of 540 nanometers. The x-axis in this graph represents the wavelength in nanometers, and the y-axis represents the fluorescence intensity. Another problem that I ran into early on was the settling behavior of the microplastics. So the fluorescence in a standard 10 millimeter cuvette is measured in the middle of the sample, as can be seen in the diagram to your left. However, because the microplastics have this tendency to settle, the microplastic fluorescence decreased over time, not because of a lower concentration, but because of the behavior of these contaminants. And this can be seen in the graph to your right, where the x-axis represents the time in minutes, and the y-axis represents the fluorescence intensity. To combat this issue, I used white flat-bottom well plates with a fishtail fiber optic attachment to make small collection or integrating spheres. The fiber optic was essentially designed to fit these wells perfectly, so it fully covers the top of the well, and the microplastics have nowhere to go, so all the fluorescence will be directed upward. Through this method, the microplastic fluorescence can be accurately measured regardless of settling behavior. I then took a repeated measure of a 0.1 milligram per milliliter microplastic contaminated solution in different wells over time, and the spectra and graph that you see before you really highlights the precision of this technique, as the 540 emission is constant regardless of location or time. Then, to quantitate the microplastics using this fluorescence technique, I created serial dilutions of the 0.1 milligram per milliliter solution and collected their emission spectra. Emission intensities were then plotted against a microplastic concentration. So now this is the proposed design of my artificial coral sponge. And as you can see, it includes a melamine sponge to act as the base, a 34% PTFE dispersion to act as the binding agent, and then calcium carbonate for microplastic capture. Additionally, in order to prevent ACS consumption and disruption, an eco-friendly enclosure will be constructed around this device. To synthesize the ACS, ridged melamine was cut into rectangular prisms with surface areas of roughly 2,000 millimeters squared. the PTFE was then sprayed and put in an oven for an hour at 60 degrees. Then, the PTFE-coated sponges were taken out, submerged in 4 grams of per 100 milliliters of calcium carbonate suspension and 10 millimolars of SDS, and then ultrasonicated for 10 minutes. Ultrasonication is vital to ensure calcium carbonate application on not just the surface of the sponge, but hopefully as well as its structure. It was then placed in an oven for the final curing at an hour for 60 degrees. I then took FTIR spectra and SEM images of the ACS at each step of its construction to provide evidence for the successful fabrication. As you can see, in the PTFE-coated sponge FTIR spectrum, the sponge is fully coated with the PTFE with no traces of melamine. The x-axis and equals wave number, and the y-axis is percent transmittant for all FTIR spectra. I then took an FTIR and SEM of the completed ACS, and the arrows that you see before you on the FTIR highlight the calcium carbonate application throughout the sponge. Microplastic remediation experiments were carried out with an ACS, along with a PTFE-coated melamine sponge and a plain melamine sponge to act as comparative controls. Each were evaluated in either microplastic-contaminated artificial seawater or microplastic-contaminated deionized water to mimic fresh water. Each configuration was then placed on an orbital shaker to simulate ocean currents, as well as provide continuous movement over the testing period. 500 microliters samples were taken out periodically for further analysis. As expected for the untreated and PTFE controls, there was little to or no loss at all of the microplastics within the contaminated solution. The ACS in seawater was able to remediate roughly 93%, and through conversion of concentration reduction, this is 0.47 milligrams of microplastics remediated per centimeter squared, or 9.3 thousand per centimeter squared. The graph on the left has an x-axis of time in hours with the y-axis of microplastic concentration. And you can see this visual decay in microplastic concentration over time in regards to the ACS as it is retaining these microplastics. Adversely, the graph on the left on the right represents percent remediation with an x-axis the same as time in hours and a y-axis of this percent remediation. Furthermore, if you look at the top, there is a picture of a clean ACS next to the ACS post 45-hour trial. And this just really shows the visual retention of microplastics as it is quite literally bright green. As for the deionized water, the ACS remediated roughly 83% with 0.4, meaning 0.42 milligrams per centimeter squared or 8.3 Ks per centimeter squared. For both the seawater and the freshwater, I found that the ACS remediation occurs rapidly for the first 9 hours and then begins to slow afterward. In addition to the fluorescent measure of ACS-induced microplastic loss in a contaminated solution, SEM and EDS analyses were also conducted to see visual absorption and retention of the microplastics after the 45-hour trial. The EDS analyses highlight the consistent presence of fluorine and calcium, and this points to ACS components like PTFE and calcium carbonate lending to stability even after prolonged use. So the SEM of the side, this is the side, it really corroborates past statements about full retention of the microplastics. Now, this is the center of the ACS post 45-hour trial, and you can see that it highlights that the ACS is not only a surface remediation device, but as well as capable of remediation throughout its structure. And now this is a pleasant surprise as it now provides this compelling evidence as to the ACS being a full remediation device. After I saw SEM images of the 45-hour trial, I realized that there was still a lot of space left for further remediation and wondered if this was the ACS's just capacity of retention or if there was still room left to go. Therefore, to test this, I made an intentionally super concentrated solution of 0.5 milligrams per milliliter and used it in 1 week to model ACS remediation lifetimes. And if you recall, this method is based on nucleation of the calcium carbonate, and I feel like this SEM really demonstrates it well. After 1 week, SEM images suggest that at full capacity, the ACS was able to retain up to 2 million microplastics per device, or 105 milligrams per device. So now that I really know that the ACS is not only a surface-only remediation device, I converted the 93% remediation in seawater into a number of microplastics, and the same with the deionized water. Compared to the SEM image of the super loaded solution, it shows that there's still room left to go before the device reaches its maximum capacity. After seeing these results, I decided to conduct alternate longevity trials to see if I could reach extended remediation capabilities. So I put a clean ACS in 0.1 milligrams per milliliter of solution and left it on the orbital shaker for 1 day. It was then transferred to a solution of the same concentration and left for 24 hours. This was repeated once more, and samples of the solution were taken out at time 0 and after the 24 hours. So these trials really highlight the possibility of reuse. So after batch 1, the ACS removed 186,000 microplastics, 170,000 the second day, and 163,000 for the last day. And as you can see, these are in line with previous results, and it points to a marginal decline in remediation, pointing to reusability until the ACS is fully retained with microplastics. Finally, trials were conducted with different shapes and builds of the ACS to see if to investigate the effect of shape on overall performance. And I found that both the cube and ellipsoid ACS demonstrated similarity in overall remediation. However, the ellipsoid did demonstrate a slower, more linear remediation in the first 10 hours, and this points to using the cubic ACS as the most rapid remediation method. To summarize, throughout this research, an accurate fluorescent microplastic detection system was established, the ACS was successfully fabricated, the ACS was able to efficiently remove microplastics in both seawater and freshwater, SCM and EDS analyses highlight this visual retention, and SCMs of the high-load long-term experiments highlight full remediation capacities. Additionally, longevity trials highlight marginal decline in microplastic remediation over several batches, and this points to reuse capability. The ellipsoid versus the cubic ACS show similar remediation capabilities. The ACS is stable and safe for marine life, and each device is only 30 cents or $12 for a device that mimics a typical 625 centimeter squared coral. I think my time might be up, but my future research would just include looking at the ACS's remediation efficiency and capability for microplastics covered with free-floating pollutants like PCBs and PHAs, as this can also cause a threat of its own.
That's time.